Hello everyone. Let's discuss contest 21, which is strange contest. So first problem kind of easy, then we have problem E, also kind of easy, but and then in the end we have three problems again from some calculated contest. So we have three problems of kind of the same topic, but they this time they are very different actually. So we have problem F and G, and then we have problem H. So they kind of similar, but not as similar as in the previous contest probably. So we'll see. I actually stuck on problem G for a long time, like you see here, like I have 3 incorrect submissions. And like it's not only me, okay, you only it's here. Okay. Strange problem. Okay, but well, okay, we'll go to it. And problem H is pretty easy, I would say. Okay, I have +1 because I'm stupid, but so I believe the strangest problem today is problem G, but we will go to it. So let's go. So the first problem is very straightforward. Okay, you have some columns and you have gravity which moves them to the right. And okay, the interesting part is to see that the set of columns is the same after you move everything to the right. Despite the fact that the operation is kind of strange, so you move not the columns but individual cubes. You put to them boxes, you put them to the right. But it's actually the same like if you just sort all the columns. No, because no, if you look at number of columns of the same height, you will see that if you move all the boxes to the right, number of columns of the same height will be the same. So this set of columns is basically the same after you apply the separation. So set of the columns is the same, but when you move them to the right, it will be sorted. Yeah. So basically, the operation we do is just sort all the columns. So this is the whole code. Basically, read the array, sort all the columns, and that's it. Interesting problem. Okay, it's easy, but again, it shows you interesting concept. Then some strange operation which applies not to the columns but to individual boxes. Actually, if you look at this operation in terms of not individual boxes but in terms of these columns, you see how this set of columns changing after the separation. In this case, just sorting. This interesting concept to think about. So in some another problems, you may see some similar things. So you have some operation which operates on some individual elements, not on stacks of elements or some sets. But if you look at this operation in terms of these stacks and columns, like here, you may see that this operation does something interesting. Yeah, like here. So this is problem A. Just sort the array. That's it. Problem B. Oh, problem B is nice technical problem. So you need you need to find the closest time, which is a palindrome. I like problems about time, but when you have like 4-digit clocks and you need to find something. Uh, it's pure technical problem. Nothing really interesting here. So many ways to do it. Basically, you just iterate over all possible time in one day. So you have like 24 multiplied by 60 possible combinations of hours and minutes. And you just iterate over all of them, find the closest, which is a palindrome. Okay, here I'm thinking about how to do it, in the most pretty way, but then I decided it's not like that. So it's again, this competition is not about the prettiest code possible. So it's competition about the fastest possible solution. So you just implement it how you can implement it. So you find the fastest way to implement it, not the prettiest possible solution. And here I'm doing something like this. So I take this input and immediately transform it to number. So because for me it's easier to work with numbers. So t is just number of minutes from midnight. Yeah. So it's hours multiplied by 60 plus minutes. And then I just make +1 to this number until I have a palindrome. So I increase number by 1, and then I need to check if it is a palindrome or not. Yes, I calculated modulo number of minutes. Yes. Here, how to check if it's a palindrome? I will just construct the palindrome. Here again, I'm thinking too much about the better way to do it. Yeah. Yeah, okay, I spent some time here. Here I will just construct the string which represents this time. And I've just constructed just character by character. Okay. Let's speed up a little. It's too slow, too slow. Op. Okay. So I just add all these 4 digits one by one. Yes. So I take one digit, another digit. It's one way to do it. Okay. Okay. If you like some another way to do it, up to you. I just find it easier to do it like this. That's it. So and then I check if it's palindrome or not, just by reversing and check that they have the same string. Just run some more tests to be sure. Oh, so here's the whole program. So again, I take my initial string, transform it to number, and then increase this number until I have a palindrome. To check if it is a palindrome, I construct the string back, yeah, reverse it, and check if that reverse string is the same. If the reverse string is the same, then I have a palindrome. Yeah, that's it. So that's it. That's problem B. Let's go to problem C. Oh, problem C is strange. Okay, so you have some boys, some girls. You need to build maximal number of pairs. So in each pair, one of the persons is taking part in the first time. And it's like just by looking on examples and thinking a few minutes. Okay, let me see. So let me show. So in every dance, I must have at least one of the persons to be dancing the first time. Yeah. So since I have n plus m persons in total, yeah, in every dance one of them should be the first time. Yeah, I should have at most n plus m dances. Yes, and in the first dance, both persons are dancing the first time. Yeah, so in the first dance, I kind of spend 2 items. Yeah, and in every dance, I spend at most at least one item. Yeah. So in total, I might have no more than n plus m minus 1 dances. Yeah. Like imagine all boys and girls have some tokens. Yeah. And when you dance the first time, you spend this token. Yeah. So in the first dance, we spend 2 tokens. In each other dance, we spend at least 1 token. Yeah. So we cannot have more than n plus n minus 1 dances. Yeah. And it's easy to build the construction with n minus 1. So I'll just take the first boy dancing with all the girls, then the first girl dancing with all the boys. It will give me exactly n plus n minus 1 dances. Again, I believe the difficulty of this problem is just to understand what's going on in the problem statement, and then just think a little of what we need to construct and how to do it. Okay, that's it. That's the whole program. Let's go to problem D. Problem D. Okay, problem D is another nice problem. So problems like these occur in multiple situations. Here we just so this variation here is pure technical, so nothing interesting happens here actually. But in some other problems, you may have similar task with some more stuff going on. So what's happening here? We have some conditions on given number. So for some unknown number, we have a lot of inequations. So inequations of form greater, less, greater, equal, less equal, something like this. Yeah. And we need to find any number which satisfies all these constraints. Yes. Difficulty here, I believe, is because we have too many stuff going on here. So we have all 4 different different signs like greater, less, greater, equal, less equal, all 4 of them. And also we have for each condition we have true or false. So for each condition we know if it is true or false. And what I'm doing here, I'm trying to simplify everything. Yes. So what I'm doing first here in the first part, I want to get rid of this less or equal or greater or equal signs. So if I have less or equal, it is the same as less of number x plus 1, because I have integer numbers. Yes. So if number is less or equal than x, it is the same if it is less or than x plus 1. Yeah. So here, so now instead of having 4 cases, I have only 2 cases, less or greater. Yeah. And here I get rid of the of this second part. So if the result is false, yeah, I transform this constraint to another constraint with true. Yeah. So if this is false, so if this was less, so and the result is false, it means it is not less. Yeah, it is not less than x. Not less than x is the same, is greater than x minus 1. Yeah. So again, I'm transforming all these negative constraints to positive constraints. Yeah. So now I get rid of all non-important details. Yeah. Now I have only constraints of type greater than x or less than x. Yeah. And now I'm solving the problem. So solving the problem like this, I maintain the segment of all possible values. So my segment from L to R is the segment of all possible values. So what I'm doing here, I'm trying to update this segment every time I receive a new constraint. So if I have this constraint of greater, it means I need to move the left border to x plus 1. If I have constraint, I move the right border to x minus 1. Yeah? So every time I update my segment of possible values. And then I check if my segment is empty. So if r is less than r, so it means there is no value to satisfy this constraint. If it is not, I pick any value from L to R. Or I pick L because I can, but you can pick any value from L to R. That's it. Nice problem. Maybe a little bit too technical, but okay. So I believe the difficulty here is to carefully take care of all the cases. And if okay, it's more about careful programming than anything else. That's it. That's problem D. Let's go to problem E. Oh, okay, problem E is actually clever problem. So what we need to do in problem E, we're looking for alternating subsequence, and we can flip a continuous substring to maximize the length of alternating subsequence. Okay, a lot of stuff happening in the problem statement. So let's write something down. So what we're looking for. So we have a string. So let's try to think what we're maximizing. We're maximizing the length of alternating subsequence. What does it mean? It means we have some subsequence. Subsequence is just some sequence of elements, which is not specific. It doesn't not necessarily consecutive. Yeah. So we can pick some. So pick 1, then we pick skip something. We pick some 0. Then we all they may be continuous also. So let's pick something 1, 2, boom, 0, then pick 1, and so on. So we have some alternating subsequence, and we want to one of the subsequence of the maximal size. So let's solve this problem first. So if I have some sequence of zeros and 1, how to find the length of the maximal alternating subsequence? No, it's easy to see actually. No, we solved problems like this before. Yeah. So when you're looking for some specific subsequence, you can do it greedily. You just go from left to right and greedily pick all the elements of your subsequence. Yeah. So how we do it? How we find the maximal length of alternating subsequence? So we just go from left to right and greedily pick elements we need. So we pick the first element, for example, 1. Then we have some elements equal to 1. We skip them. Then we pick element 0. So we pick this element. Then we pick this element. Then we have some zeros. We skip them. Pick the element 1 again, and so on. So we pick this element and so on. Yeah. So basically, what's happening? We have some groups of equal elements. And from every group, we can pick only one element. So length of longest alternating subsequence is just equal to the number of these groups of equal elements. Okay. So again, if you have sequence like this, again, if for 1 0 0 0 0 0 1 0 0 1 1 1 0. Yeah. So we just look at this sequence, look at the groups of equal elements. Yeah. From every group, we can pick only one element. Yeah. So the maximal length of alternative sequence will be 1, 2, 3, 4, 5, 6, 7. Yeah. So we can pick 1, 0, 1, 0, 1, 0, 1. So this is the longest alternating subsequence we can get. Okay. Okay. This is the first part of understanding the problem statement. Yeah. So we just understand how to find this maximal alternating subsequence. Now let's go to the second part. Now we need to find the substring that we will flip. Yeah. And after this flip, we want to maximize the length of the sequence. So let's see. So what happens if we flip some substring? So if I take substring, let's say from here to here. No, let's say from here. Let's say okay. Let's say to here. Yeah. Okay. And flip this angle. So like 1 1 0 1 1. Yeah. So I flip this part, and everything else stay the same. 1 1 0 0 1 1 1 0. Yeah. So I have 1 1, then I have 0 0 1 1 tuk 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 tuk. So you see, I go from this to this. Yeah. So what did change? What changed in this like block structure? So here, when block started, I have new split between two blocks. You see? So here, when I start the segment, yeah, you see? Now there is a new border between two blocks. Yeah. Why it happened? Because I flipped this item but didn't flip this item. So they did belong to the same block. Yeah. But after I flip this substring, they belong to different blocks. Okay. What happened here? Again, if my border is already between some segments, some blocks of equal elements, yeah, so I basically remove this border here. Yeah. So how did this number change? Number of blocks. So I'm maximizing number of blocks. Yeah, because length of this alternate subsequence is the same as number of blocks. So if I want to maximize number of blocks, yeah, I want to build the segment in such a way that both borders of the segment are not between two blocks. Yeah. So if I put the border not inside the block, like here, I create a new border here. Yeah. And if I put my end of the segment between two segments, like here, yeah, I basically remove this border between the blocks. I merge two blocks into one. Yeah. So here I split the block. Here I merge the blocks. Yeah. And if I want to maximize number of blocks, I want to split both blocks in both ends of my segment. So the optimal way will be to make, for example, something like this. So both ends. So this is 0. This is, yeah. So now this border stays the same, and this I create a new border. So I will create a new border here, and I will create a new border here. So I split this segment, and I split this segment. That's it. So what I will do, I will calculate how many points of this type I have. If I have at least 2 points of this type, I can put my segment between them and increase number of segments by 2. If not, I can increase it by 1 or by 0, like this. You will see. So let's go. So so here I'm just counting number of blocks. So R is number of blocks. let's stop here. So I count number of blocks like this. So I go from left to right, and if I see the beginning of the block, so the first point of the block is either point 0 or the point not equal to the previous point. Yeah. So R is just number of blocks. Now I count number of interesting points. Interesting points is where I can put the border of my segment and increase answer by 1. Here. Okay, here I'm carefully reading what's happening with the ends of the segment. Can I split? Can I flip empty segment, for example, something like this? Okay, okay. So the okay, back. So actually, answer just looks like this. So I have R is my initial number of segments, yes, and I can increase it by minimum of B and 2. So if B is at least 2, I can increase number of blocks by 2. Yeah. If B is equal to 0 or 1, I can increase it by 0 or by 1. Yeah. Now B equals 0 is just mean my whole sequence is alternating. I just can flip the whole sequence. If B equals 1, it means I have 1 point. I can flip segment from this point to the end of the segment and increase number of segments by 1. Okay, hope it's clear enough. So that's basically that problem, this problem E. Interesting problem, solution is kind of short. Okay, now we move into last 3 problems about zombies. Okay, problem F. Okay, problem F and problem G introduces you the strategy, how it all is going on. So we have some zombies. They again quite popular problem in mathematical in math Olympiad society, I believe. So in community. Basically what's happening. So we have some number of people and they trying to divide some treasure. Yeah. So we have some treasure and they divide it like this. So the first person suggests some way to split the treasure, and then everybody votes. Yeah. And if they vote for this concept, then they just agree and we stop here. If they vote against this suggestion, then we kill the person who suggested it and continue to the next person. Yeah. And basically the strategy for every person is like this. Every person is want to survive first, and if it is possible to survive, they try to get as many brains in this case as possible, so as much treasure as possible. Quite again, it's quite well-known problem for Olympiad math community, but again, I struggled too much solving this problem today. I'm not sure why. Yeah, basically, I think I know how this system works, but I'm not sure how to calculate this result. So I spent too much time calculating for problem G. Okay, in the first problem, we just need to find we need to find the maximal number of brains we need in the beginning, so we can survive and we have at least 1 brain for ourselves. Okay, let me okay, this long problem statement, I read it very carefully because who knows what happened here. And okay, and then I start drawing. Okay, so I just so what I'm doing here, I'm just playing with this concept and start and think what's actually going on. So when I have when I have 2 persons, the second person can get 1 brain for himself and 0 for the next one. If I have 3 persons, I can arrange it like this. If I have 4 persons, I can arrange it like this, and so on. So I basically try to play with some small values and just see what's going on. Okay. And then I see that the answer, so answer always look kind of like this. Okay, maybe it's not quite clear what I'm writing here. Let me stop here. So let me draw you another picture. So if I have only, so again, what is the plan? So if you have n persons, so if I have n persons, yeah, so this is me, I am the last one, yeah, so I'm suggesting some way to divide the treasure, yeah. So what is my suggestion? I will take one coin for, okay, one brain for myself. Okay, let's split coins, not brains. It just sounds less scary. Okay, so I will take one coin for myself. Then I will give some coins to these persons. Yeah. So here I have 6 persons, so I need at least 3 votes. Yeah. So I will vote, and I need some 2 other persons to vote. Yeah. So from these persons I need to okay, I need to persuade at least 2 of them to vote. Yeah. Okay, let's try. Which one? Okay, let's see. So if they killed me, so what will happen here? Here I will have 5 persons. Yeah, and this person will give them something. Okay, and if they didn't kill me, then I have this person. Okay, so let's go to the very beginning. So here, imagine I have 1 coin for myself, and I will give 2 coins to someone else so they can vote for me. Yeah. So imagine I have 3 coins. Yeah, for simplicity. So let's just think what will happen in this game. So if I have 3 coins, then if we kill everyone and only 1 person left, so he will take 3 coins for himself. If I have 2 persons, then this person can take 3 coins and give 0 here, and vote for himself and win. Yeah? If I have 3 persons, then this person, yeah, he need 2 votes to win. Yeah, so 1 vote from himself and another vote from one of these persons. Yeah, so he need to kind of bribe one of these 2 persons. Yeah? So what about these 2 persons? So if they kill him, they will get 0 and 3 coins. So if we did so these 2 persons, they think, if we vote against this proposition, yeah, so if we kill this person instead, yeah, then we will have this situation, and we know how this situation ends. So this situation ends with this person receiving 0, this person receiving 3. Yeah, so we need to bribe some of them to get 1 extra vote. Yeah, and easier to bribe this person, because now he receives only 0 coins. So if we give them 1 coin, this person will vote for us. Yeah. So now we have 2 votes. This person we doesn't need. We don't need this person. So let's just give them 0. Yeah. And leave ourselves all the extra coins. And just continue thinking about this, just layer by layer. If we have 4 persons, again, we need 2 votes. We have 1 vote from us, and we need another vote from one of these persons. Let's see who it's easier to bribe. It's easier to bribe this person, because if this person decides to kill us, he will receive 0 coins. Yeah. So let's bribe this person. Let's give them 1 coin. Yeah. And again, nothing to this two. And I'm going to continue here. Here we need 2 votes, 2 extra votes. So we will vote for ourselves, and we need 2 extra votes from these people. And it's very interesting. We have 2 persons with 0 coins. We can give 1 coin to each of them. Yeah, and 0 coins to all of them. Yeah. And that's it. And here again we need 2 extra votes, and we have 2 persons who receive 0 coins. So let's give 1 coin to each of them. So this is the final answer. That's it. So it's easy to see that the structure is something like this. We have this like chessboard style colored picture. You see, you have these zeros, and number of non-zeros equal to like half of all the numbers. Mhm. So that explains why the answer is like half of the answer. Okay, I will just pum 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 like this. So that's it. That's the solution for problem F. It's kind of easy looking solution, but again, there is a lot of thinking going on when you submit something like this. And also this all this, let's say, insight will help you for the next problem. So in the next problem we have all the same thing, but we don't need to have this one extra coin for ourselves. So we need to find minimal number of coins we need to just to survive. And at first, okay, I spend a lot of time because I'm doing something. Okay, you'll see. So at first I see like this number is like one less than we need before. So it looks like situation is kind of similar to before, but we just don't need this one extra token, one extra coin for ourselves. Okay. 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 I thought it's kind of trap. Yes, it shouldn't work. You see, but I tried it anyways because it shouldn't work, right? It can't be that easy. Okay. Now I go back to problem, and then again, that's something I noticed even before, but here I try it once again. All the numbers in these examples are odd. Yeah. So I thought that something strange should happen with even numbers. I just not sure what exactly. So again, I spent too much time. I spent too much time here. I'm thinking what's going on. Okay, looks okay. It all looks okay. Okay. No. Here I thought the following. I thought that if I have 4 coins, then I don't need any coin. If I have 4 people, I don't need any coins, because if I have 4 people and I have 0 coins, if I have 0 coins, then okay, I have 4 people. I can just assign them like this. Then I will vote for this concept. I like this concept, and this person will also vote for this concept. Yeah, because if this person vote against, then I have situation like this, and we will kill this person. Yeah. So I will vote for this concept, and this person will also vote for this concept, for this proposition. Yeah. So if I have 4 people, I need 0 coins to win. I just suggest to split it as all zeros, and this person will vote for me. And I have at least 2 votes, and I will win. And I thought it's kind of works for all even numbers. So for all even numbers, answer is 0. It's not. Okay. Okay. Um, okay. Here I spend a lot of time actually thinking about what is the correct. Okay. This problem killed me. I spent too much time drawing all these pictures. Uh, okay, I tried some formula just because I was too tired, and then I decided, okay, it's enough time I spent to trying to guess the formula. Let's just simulate. Yeah. So what I will do, I will just simulate this process and run a brute force to find these numbers and then look at them. Maybe these numbers looks like so maybe you can look at these numbers and just guess the formula. Yeah. So again, instead of drawing all these pictures, I will write the program, yeah, which just finds all the optimal numbers using brute force. That's something I actually do a lot. So when I feel like there should be some formula, but I am not sure which one exactly, or when I think there should be some pattern, but I don't know which pattern. Yeah. So sometimes it's easy to just generate some answers and just look at them. So that's what I'm doing here. It's actually surprisingly not that easy to do in this problem. So I'm doing actually the same as I told you before. So I'm trying to build, so here n is number of people and s is initial number of coins. So I fix number of coins and try to simulate this process. So when I have one person here, A0 is when I have only one person. This person just received all the coins. Yeah. So AI will be the final like say so if I have this number of people and this number of coins, what will be the final configuration we get in the end? So AI is the final configuration if I have like I plus one people and S coins. Okay, hope it's clear now. So what I'm doing here, I'm trying to construct the answer. Yeah. So here, I look at the previous result, sort it, because I don't care about the sequence. Yeah. Now I take some first people which received the smallest amount of coins and try to bribe them. Yes, to get their votes. Yeah. And I need to get at least these plus one votes. Now, if I have not enough coins, then okay, I cannot bribe all these people. Yeah, so I cannot make the proposition which will satisfy everyone. Yeah, so they will kill me. Yeah, so my final configuration will be the same as the previous one, plus I will be dead. So my amount of coins will be -1. -1 is just a nice amount of coins because I can bribe myself by giving me 0 coins. Yeah. So this person can be bribed by giving 0 coins. Yeah. So if it now he receives -1 coins, I will bribe him by giving 0 coins. If it's not, if I have enough coins, I will bribe all these people and give 0 to everyone else. Yeah. So I will iterate all these people again. So I iterate of first half of people, give them this amount +1, and then I will give 0 to everyone else. And then I will give myself all the rest coins. So X, I spend X coins bribing all those people. Then everything else I will give to myself. Okay, and this will be my final configuration. And then I'll check if the last person survives. Yeah, so if the last person received non-negative amount of not -1, then this amount of coin is enough for the last person to survive. Yeah. See, that's it. So I'll just print the minimum. So S is the minimal number of coins which is needed for n players to survive. And then I just run and see. Okay. This doesn't look very promising. Okay. By looking at this sequence, you probably cannot find anything interesting. But again, I remember that it should be kind of different for odd numbers and even numbers. So I built separate sequences for odd numbers and for even numbers. Okay, for odd numbers, this looks promising, you see? So this is sequence for all odd numbers. It's actually look like what we did before. Yeah, it's like half of n. We actually tried these numbers before. And the problem indeed is only with even numbers. So let's look at the even numbers. Okay, let's look interesting. Okay, let's see. So you have 0, 1, then 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay, you may already find the pattern. See? So the pattern is strange. I'm not quite sure why it's like this, but okay. Here again, it's not always necessary to understand why your solution works. Okay, you need to write a program which produces the correct result. So now in my case, I see that I have zeros in positions equal to powers of 2. You see, so I have zeros in position 1, 2, 4, 8, 16, and so on. Yeah, I'm not sure why, and I don't need to. Yes. So I just need to find the correct formula. See, I look at all these zeros. I see that all the zeros are in positions equal to powers of 2. And I just believe it should be true for all the next numbers as well. We can think about why it's actually correct, but I actually don't want to. It's probably, if you think about it for a long time, it kind of makes sense. I don't want to. Here I want to try what is the constraint for number n. So int should be enough. So if it's 2 multiplied by, if it's 2 billions here, I don't want to multiply it by 2 because I have 4 billions. I have integer overflow. Just double check. And that's it. So that's problem G. No idea why it works actually, but that's the solution. Okay, you can think about it. Write in the comments if you know why it works. Final problem. Problem H is a little bit different from all the previous problems. So in previous problems we need to split some treasure, and here we have another kind of cooperative game. It is another pretty famous problem. So it works like this. We have some number of people. They see all the numbers except their own. Yeah? And they make a guess. So and they make it simultaneously. All people try to guess the number simultaneously. And if at least one of them guesses number correctly, then they win. Okay, it's quite popular problem. Let me show how to solve it. It's okay. If you never saw it before, you can stop the video here and think about it. It's not that hard to solve. So we have some people, and they need to find the number written by the head. So imagine, so you know all the numbers except your own. So let's see. So we have n people, and we have numbers from 0 to n minus 1. So in this problem, they are from 1 to n, but it doesn't matter. Let's shift it one position so it's easier to think about it. So let's look at the sum of all the numbers modulo n. So if we know this sum, if we know this sum, we can calculate our number. If we know all numbers except 1, we can find this number. Yeah. So each number ai will be s minus sum of all j not equal I ai, yeah, modulo n, like this. So if we know what the value of the sum, like this, so it's all in modular arithmetics, but it's actually easier to think without modular arithmetics. So if you know the sum of the numbers, and you know all the numbers except 1, you can calculate this single number. Yeah. Here we do the same, but we calculate all the sums modulo n. But idea is the same. Now, problem is we don't know this sum, but we need to now we have n persons. We need at least one of them to guess the sum. Yeah. No, they can make n guesses. And number s is number modulo n. So s is the number from 0 to n minus 1. So if each person picks one of the values of s, at least one of them will be correct. Yeah. So here I will pick number of s equal to the index of my rank of my person. Yeah. So this r is my rank. I pick x equal to r minus 1. It is my sum. Then I will subtract all other integers from this number. Yeah, and that's it. And that's it. So the strategy is like this. Every person knows its number. Yeah. So if I know my number, I make the guess that the sum of all integers equals to my number. Mhm. And if I guess the sum correctly, I can calculate my number. I can calculate no, my label correctly. Yeah, that's it. So at least one person will guess the sum. So this person will guess its label. Yep. So that's it. Kind of strange contest, I would say, but well, that's it. So that's it. That's contest 21. Thank you. See you next week.